Our solar system, a cosmic ballet of planets, moons, and asteroids, gracefully orbiting our sun. It's a place of predictable rhythms, where gravity orchestrates a cosmic waltz that has played out for billions of years. But what if this delicate balance were to be shattered? What if, without warning, a silent, ravenous predator, a black hole, materialized within our cosmic neighborhood? Today, we're going to embark on a thought experiment, a journey into the heart of cosmic horror. We'll explore the terrifying implications if a black hole, specifically one with a mass comparable to our own sun, suddenly appeared in our solar system. We'll delve into the physics, the chaos, and the chilling possibilities that would unfold, focusing on the insidious power of tidal forces, the catastrophic disruption of planetary orbits, and the bizarre, mind-bending distortions of light. Imagine, if you will, a quiet Tuesday. Earth spins on its axis. Life continues its relentless march, utterly oblivious. Then, a ripple. Not a sound, for in the vacuum of space, sound does not exist. But a gravitational tremor, an unseen hand reaching out, tugging at the fabric of reality. Our black hole, let's call it Apollyon, has arrived. The first, most immediate, and utterly devastating consequence would be the brutal dance of tidal forces. Picture our Earth, a relatively small sphere. When a massive object like a black hole approaches, the gravitational pull on the side of Earth closest to Apollyon would be significantly stronger than the pull on the far side. This difference in gravitational force creates a powerful stretching effect, a cosmic tug of war. Think of it like this. If you stood on a giant's hand and it squeezed, your body would feel pressure from all sides. But if that giant were pulling your head up and your feet down simultaneously, you'd be stretched. That's essentially what tidal forces do, but on a planetary scale. If Apollyon were to appear, say, within the orbit of Mars, the tidal forces exerted on Earth, even from that distance, would be immense. Earth would begin to deform, its perfect sphere subtly elongating towards and away from the black hole. This isn't a gentle stretch, it's a monumental stress. As Apollyon drew closer, the tidal forces would intensify exponentially. Oceans would bulge dramatically, creating colossal tidal waves that would dwarf any tsunami in recorded history. These aren't just surface phenomena, the very crust of the Earth would groan and crack under the immense strain. Volcanic activity would skyrocket, earthquakes of unimaginable magnitude would tear through continents, and the planet's internal structure would begin to liquefy and churn. The effect wouldn't be limited to Earth. Every celestial body in the solar system would be subjected to this agonizing stretch. Jupiter, with its immense mass, might initially seem more resilient, but even its gaseous envelope would be pulled and distorted into an egg-like shape, its great red spot perhaps twisting into something far more chaotic. Moons, with their weaker gravitational self-binding, would be particularly vulnerable. Consider our own moon. If it were to pass too close to Apollyon, the tidal forces could easily exceed its own gravitational cohesion, tearing it apart into a spectacular yet terrifying ring of debris. This wouldn't be a gentle disintegration. It would be a violent, explosive unmaking. Imagine the horrifying spectacle from Earth, our familiar lunar companion transforming into a glittering, deadly halo of rock and dust, each fragment a potential projectile. But the real horror of tidal forces comes when an object crosses the Roche limit. This is the critical distance from a massive body where tidal forces overcome the self-gravity of a smaller orbiting body, tearing it apart. For a solar mass black hole, the Roche limit for rocky planets like Earth would be relatively close, but still within the solar system's inner reaches. If Earth, or any other planet, were to stray within this boundary, its fate would be sealed. The planet would be ripped asunder, not in a single cataclysmic explosion, but in a gradual yet utterly relentless process of spaghettification. Yes, spaghettification, a term coined by astrophysicists to describe the fate of objects falling into a black hole. As a body approaches the black hole, the gravitational gradient across its length becomes so extreme that it is stretched out like a piece of spaghetti, longer and thinner, until it ultimately disintegrates into a stream of individual atoms. Imagine witnessing this. A planet, once a vibrant world, slowly but surely pulled apart, its mountains and oceans elongating, its core exposed until it becomes a thin, incandescent stream of plasma spiraling into the abyss. This would be the ultimate cosmic horror, a testament to the brutal, unforgiving power of a black hole. Now let's turn our attention to the second major consequence, the catastrophic disruption of planetary orbits. Our solar system is a finely tuned clockwork mechanism, each planet's orbit a delicate balance between its own inertia and the gravitational pull of the sun. Apollyon's sudden arrival would be like throwing a wrench into this celestial machinery. The sun, being by far the most massive object in our solar system, dictates the gravitational landscape. However, a solar mass black hole, by definition, has the same gravitational pull as our sun. If Apollyon were to appear, it would instantly become a second, equally powerful gravitational center. The immediate effect would be the creation of a new, unstable binary system. The planets, accustomed to orbiting a single star, would suddenly find themselves subject to the competing gravitational tugs of both the Sun and Apollyon. This wouldn't lead to a simple realignment, it would lead to utter chaos. Planets would be pulled from their stable elliptical paths. Orbits would become erratic, highly eccentric, and dangerously unstable. Imagine Mercury, currently zipping around the sun in a tight embrace, suddenly experiencing a powerful pull from Apollyon. Its orbit would stretch, perhaps sending it hurtling towards the sun, or worse, flinging it out of the solar system altogether. Earth's fate would be particularly precarious. Its orbit, a near-perfect circle, would warp and distort. We might find ourselves on a trajectory that swings dangerously close to Apollyon, facing spaghettification. Or we could be flung into the outer reaches of the solar system, turning our temperate world into a frozen wasteland. Alternatively, we could be sent on a collision course with another planet, a cosmic game of billiards with catastrophic consequences. The gravitational interactions would be incredibly complex, a chaotic dance of pushes and pulls. Some planets might find themselves in stable, albeit new, orbits around either the Sun or Apollyon. Others might be ejected from the solar system entirely, becoming rogue planets wandering the interstellar void, their chances of supporting life extinguished. Consider the asteroid belt and the Kuiper belt. These regions are teeming with countless rocky and icy bodies. The gravitational turbulence caused by Apollyon would stir these regions into a frenzy. Asteroids and comets, once relatively stable, would be flung inwards, creating a deadly bombardment of the inner planets. Earth would face an onslaught of impacts far exceeding anything in its geological history. The very concept of a year or a season would become meaningless. Our planet's tilt, responsible for the seasons, could be drastically altered or even completely inverted. Days and nights would become unpredictable, temperatures would fluctuate wildly, and the delicate climatic balance that sustains life would be shattered beyond repair. Even if Earth somehow managed to avoid direct collision or spaghettification, the sheer instability of its new orbit would make sustained life virtually impossible. Extreme temperature swings, increased radiation from a chaotic magnetic field, if it even survived, and the constant threat of impacts would render our planet uninhabitable. Finally, we arrive at the most visually stunning, yet equally terrifying consequence: light distortions. Black holes are not just gravitational behemoths, they are also cosmic lenses, bending and twisting the very fabric of space-time around them. This has profound implications for how we would perceive light, and thus, reality itself. Imagine looking towards Apollyon. You wouldn't see a black void in the conventional sense. Instead, you'd witness a bizarre and mind-bending phenomenon. The light from stars and galaxies behind the black hole would be bent and focused around it, creating a shimmering, distorted halo of light known as the Einstein ring. This isn't a solid object. It's a visual effect caused by the extreme gravitational lensing. You would see multiple distorted images of the same distant star stretched and smeared across the sky. The familiar constellations would be unrecognizable, their stars seemingly dancing and swirling in impossible configurations. As Apollyon drew closer, the distortions would become even more extreme. The region immediately surrounding the black hole, the event horizon, would be a point of no return, where gravity is so strong that not even light can escape. This would appear as a perfect, impenetrable sphere of absolute blackness, absorbing all light that crosses its boundary. But the weirdness wouldn't stop there. Light from the sun, our life-giving star, would also be affected. If Apollyon were to pass between Earth and the sun's image would be dramatically distorted. You might see multiple suns, or a single, highly elongated and warped sun. Its light, vital for photosynthesis and warmth, would be scattered and diluted, leading to a profound darkening of our skies, even in broad daylight. Furthermore, the very concept of time would become distorted near Apollyon. According to Einstein's theory of relativity, massive objects warp space-time, and this includes time itself. As you approach the black hole, time would appear to slow down for an outside observer, while for you, time would continue normally. This phenomenon, known as gravitational time dilation, would mean that if you were somehow observing someone falling into Apollyon, you would see them appear to slow down and freeze just before crossing the event horizon, their light reddening until it vanished. The effect on our navigation and communication systems would be devastating. GPS satellites rely on precise timing and line-of-sight communication. The extreme gravitational distortions would scramble these signals, rendering them useless. Astronomical observations would become impossible, as the black hole's presence would warp and obscure everything in its vicinity. Even the color of light would be affected. Light moving away from the black hole would be redshifted, meaning its wavelength would be stretched, making it appear redder. Conversely, light moving towards it would be blue-shifted, appearing bluer. This would create a spectral kaleidoscope of colors, a beautiful yet terrifying visual representation of the universe being torn apart. Imagine trying to comprehend this new reality. The familiar sky, once a source of comfort and wonder, would transform into a chaotic, hallucinatory panorama of bending light, shifting stars, and a gaping maw of absolute darkness. It would be a visual assault on our understanding of physics and a profound psychological challenge. In conclusion, the sudden appearance of a solar mass black hole in our solar system would not just be a catastrophic event, it would be an existential nightmare. The brutal power of tidal forces would tear planets apart, reducing them to streams of subatomic particles. The delicate ballet of planetary orbits would descend into a chaotic mosh pit, flinging worlds into the cosmic void or towards fiery destruction. And the very fabric of light and time would be twisted and contorted, presenting a distorted, terrifying reality that would shatter our perception of the universe. It's a chilling reminder of the immense power of gravity and the fragile, yet miraculously stable haven that our solar system provides. So, the next time you look up at the night sky, take a moment to appreciate the cosmic order, for in the vast, indifferent universe, the unexpected arrival of a black hole serves as a stark reminder of our tiny, precious place within it. And perhaps it's a good thing that some cosmic horrors remain confined to the realm of our imagination.